which is surface energy. Okay, we talked about surface potential, surface charge. Let's talk about surface energy. If you take any surface, okay, let's take a cross section of a surface. Now you have an atom that is buried inside in the bulk of the matter, and you have surfaces, atoms that are on the surface. Okay, what is the difference between these two atoms? One is, if you take this atom, I'm just drawing the number of interactions it is undergoing with the neighboring atoms. Okay. On the other hand, I'm drawing the number of interactions it's undergoing with the neighboring atoms for the surface atom. Obviously, between these two atoms, this huge set of interactions is unsatisfied for this atom on the surface, and that is the source of surface energy. Okay. Now you have these atoms that are more reactive than the atoms inside because they have unsatisfied bonding interactions. And now the source of these interactions can be as follows. Okay. One is van der Waals interactions. You don't have to go in depth into these, but it will help you understand better. Okay. Van der Waals interactions are universal attractive interactions between any two species. You bring any two atoms next to each other, they will have van der Waals attraction. But there might be other repulsive forces, so that the net interaction might be repulsive, but there will always be this component, the attractive van der Waals component. Okay? It's because of change in fluctuating electron dipole moments. It's a much more complicated concept to understand. But just keep in mind that it's universal attractive force. Now you also have acid-base interactions, which is interaction between nucleophilic and electrophilic groups. The difference between these two is, in this case, the atoms have, the electron shells have to be actually in contact. In this case, they can be a bit far away. It's electron density fluctuation and the effect of field propagating through space. Okay, so for the van der Waals forces, the atoms need not be physically touching each other. Acid base, yes, they should be touching each other. And then, yeah, so that's what it says. It's, van der Waals forces are important if distances are more than 1 angstrom. There are also electrostatic interactions and double layer interactions, positive attracting negative. Okay. So now these are some formulas which show the relationship between the distance and the magnitude of interactions. Okay, not very important, but we need to keep in mind that the relationship is r power 6 and r power 12. Okay, so it falls off very rapidly. If you remember the electrostatic interaction, that falls 1 over r square. Okay, so electrostatic interactions fall less rapidly as a function of distance. By electrostatic interactions, I mean Coulomb. If you check your Coulomb's law, you will see that it's 1 over r square. Okay, so yeah, at larger distances, let's say more than few nanometers, you have the acid-base interactions that are negligible, and the most important interactions will be the electrostatic interactions and the van der Waals interactions. Okay, acid-base interaction, as I said, it's because of electron-rich species interacting with electron-deficient species. So there is a donation of electron, and there is contact of these two species, physical, chemical contact. Okay, now how do we quantify surface energy? So let's take two species, two types of matter which have surfaces. One is a liquid surface, the other is a solid surface. Let's start with liquid. Okay, before we go into liquid, I will just mention one property of surface energy. For example, if this is a crystal, okay, the surface energy of some materials, they depend on the previous state of the matter. I will explain what I mean. For example, if you take this crystal, if you cleave it in this plane, the resulting two surfaces, the surface energy of that, when compared to when you cleave in this direction, where the surface atomic arrangement is different, the surface energy of the resulting two surfaces in this case will be different from this. Okay, this is one property where when you're creating new surfaces with crystals which have regular arrangement, it is very important in what direction you cleave. Okay, but in the case of amorphous surfaces, substances, you can break in any direction and it will be pretty much the same. Okay, measuring surface energy. First, let's deal with liquids. The way we measure surface energy is we create new surface, and depending on how much energy we spend creating new surface, that is actually surface energy. Does that make sense? Does that definition make sense? What you do is, let's say you have a pre-existing surface, you stretch the surface so that more molecules from the bulk come into the solution, into the surface. So now the energies that you spend to create a unit area of surface, that energy is defined as surface energy. And here we create new surface by different ways. One is using a plate, where you dip a plate in a solution and then pull it out. You apply a force, you know the length, and you measure the angle that the liquid makes at the contact point, and we have a relationship between this is gamma, okay, and it's the symbol for surface energy, and it has a unit of joules per meter square. The reason why it's joules per meter square is because surface energy is measured as a function of how much energy you spend in creating a unit area. Okay, that's why it's joules, energy spent per unit area, the area that you create. The same can be done using a ring. Here I'm showing a cross section, so you take a ring, dip it inside a liquid and pull it up. Okay. And here again you have an angle made by the liquid with a tangent to the ring cross section, and you can measure the surface energy with these two techniques for liquid. Okay. Now for solid, the way you do that for solid is you take a set of liquids. You take a set of liquids whose surface energy is already known from this technique. So you take liquids and then you measure the surface energy of that, and then you take a known liquid, put it on a surface, and you measure the angle it makes with the surface. And depending on the angle, you can calculate what is the surface energy. And the logic behind this is, if you take a drop of liquid, okay, here I'm showing the cross section. The interaction between the liquid and the surface depends on three things. It's an equilibrium between three components. One is the solid gas surface energy, which is the interface. Okay, now you have three interfaces here. One is the interface. Interface is a boundary between two faces. Okay, that's called an interface. And each interface has energy, interfacial surface energy. So now you have gas, you have solid, you have liquid, you have solid. They are in contact. Now this interface is solid-liquid interface, and the surface energy of that is gamma SL. And you have liquid in contact with gas, okay, and its interfacial surface energy is LG, gamma LG, and also so is gamma SG, which is solid gas interfacial free energy. Now the relationship between the angle the liquid makes with the surface and these three components is called the Young's equation. Okay, now the contact angle, if the liquid has very high affinity for the solid, it will become highly cohesive with the solid, and the contact angle will be as low as it can be. On the other hand, if the liquid has very low interactions or very little interactions with the solid, the liquid will try to be with itself. It won't try to interact with the solid, so it will become almost a sphere. That will have a very high contact angle. Okay, here is the equation, a more detailed equation where we split the Young's equation into its components. Okay, so now we have the surface energy of the liquid related to the angle it makes with the solid, and we are splitting the total surface energy into three components. One is the van der Waals component, second is the acid-base component. The acid-base component, it can be electron donor or electron acceptor. So here you have gamma S plus, which is electron donor component of this solid, and gamma S minus, which is the gamma S plus is the electron acceptor component. These notations are here. I'm just trying to tell that from my memory. Okay. So S plus is electron acceptor, and S minus is electron donor. Okay, I'm sorry for confusing. Okay, so now here are some examples. Okay, so water has these properties, formaldehyde has these properties, and bromonaphthalene has these properties. Now, if you see, you have an equation with 3 variables. Okay. Now, for solid, you don't know what is gamma SD, gamma S plus, gamma S minus. 3 variables. But you for liquids, which have been studied using the previous method that I told, you know the components of liquids. So what you can do is, you have 3 variables. If you get 3 equations, you can solve them. 3 simultaneous equations, and you can get the individual values of 3 parameters. Okay, you understand that? It's simple mathematics. So all that we need to do is measure the contact angle on a solid surface. Let's say you want to measure the surface energy of this board. All that you need to do is take this board, measure contact angle of water on that, measure contact angle of formaldehyde on that, measure contact angle of bromonaphthalene. Okay, and you have 3 equations. For each solvent you have 1 equation, for water 1 equation, for formaldehyde 1 equation, for bromonaphthalene. You solve these 3 simultaneous equations and you get 3 variables. Okay, which is the gamma SD for the van der Waals component, the electron acceptor component, and the electron donor component. Okay, now let's say we have surface energy properties of a surface. Okay, how do we use it to predict properties of some materials? Okay, let's say you are studying, you want to predict beforehand if these 2 surfaces, let's say you have surface A and surface B, and you're going to join them, and you want to predict, will they adhere to each other? Can we do that beforehand? Can we do that even before making that experiment, visually seeing if they're combining? The way to do that is the net interaction between these 2 surfaces involves the following. First, you have the interface 1 and you have interface 2. When they join, they form a new interface. Okay, they form interface 1, 2. And overall, the process is about these 2 interfaces vanishing and a new interface being formed. Okay, all that you need to do is study the interfacial free energies before the addition process and after the addition process. And if it's second law of thermodynamics. Okay, this is second law of the thermodynamics. If the net change in free energy is negative, then the addition will happen. If it is positive, it won't happen. Okay, so for the first time, people had a way to predict theoretically, before even performing the experiment, if 2 materials can actually bind or not. And the way we do that is, we first take one surface and then calculate the van der Waals component of that, and then we calculate the acid-base component of that, and then you measure the van der Waals and acid-base component combined together as the total surface free energy of this interface, the new interface that is being formed. And if the overall interfacial free energy of the new interface being formed, if that is positive, then the addition won't happen. If it is negative, the addition will happen. So now, if you take 2 surfaces, and if you want to predict, if somebody gives you 2 surfaces and tells you, can you predict if these 2 will adhere to each other or not? The way to do that is, first measure contact angle on these, okay, and then split them into these components and measure cationic and anionic charges, okay, or measure zeta potential. If you combine these 2 information, so you calculate the interfacial free energy and then you calculate the electrostatic interactions, combining these 2 you can predict whether 2 surfaces will adhere or not. Okay. So this is a very simplistic theoretical way of predicting how colloidal particles or surfaces interact with liquids, surfaces interact with other solids. Okay, even some other properties that are important are magnetic and gravity. Okay, now we have seen how chemistry of a surface in terms of van der Waals interaction, electron donor, electron acceptor affects surface energy. Okay, now let's also see how physical property of a surface interacts, decides surface energy. Now if you take a lotus leaf, you have these protrusions that cause surface roughness. And when you put a drop of water, for example, the reason why the contact angle is very high is because there is air in between, air lock in between. And so a bit of surface that the solvent is interacting with is actually not the surface itself, but the air. So the interfacial free energy here is not just dependent on the liquid and the surface, but it also depends on liquid and the gas here. So this is one example where we also use surface roughness, physical property, to change the surface energy of solids, surfaces. Okay, here I'll give an example, okay, how to combine all this. Okay, how, let's say you have a bacteria, okay, and let's say this bacteria starts clogging your tap system in your water supply, I don't know what you call that, whatever, drinking water supply pipe. Okay, let's say this bacteria is growing and you want to build a pipe, a surface that doesn't interact with the bacteria. Okay, so now the way you go around doing this is, first you need to understand what is bacterial surface. Okay, you need to understand in terms of surface energy components. Okay, so now what we do is you make a surface out of bacteria mat, and then you measure contact angle, you measure for the individual bacterial cells, you measure the surface charge. Okay. That's what, for further information you can refer to this. But here I've summarized their results. For example, what they do is, as I told before, you have three components that you need. Van der Waals component, an electron donor component, electron acceptor component. Okay, so you need three variables. So you measure three contact angles using three solvents: water, diiodomethane, and formaldehyde. They missed the L here. It's formaldehyde. No, sorry, it's formamide. So they're right. So you have three solvents. You get three equations. You solve three simultaneous equations, and you get the van der Waals component, electron donor component, electron acceptor component, electron donor component, and acid-base component. Okay, it's that simple. And they also measure the zeta potential, where in water, in a buffer. Okay, so they both have, there are two different bacterial species they are comparing. Now, based on this, you can tell they both are negatively charged. So now, if I give you a surface, and if I ask you, will this surface bind to this bacteria more or this bacteria more? All that you need to do is take the surface, measure these components. Okay. For example, this is what they are doing here. Okay, they take a polypropylene surface, a Teflon, a glass, a silicon. Okay, and using the same contact angle measurement technique, they measured different components. And all that you need to do is take the surface energy parameters of bacterial surface, surface energy parameters of any of this, and then plug in this. And if the net delta G, change in free energy, if it is positive, then the bacteria won't stick. If it is negative, the bacteria will stick. Okay, you get the overall idea, right? So how you go from surface to surface energy components, and then that is based on contact angle. And then you take another surface, do the same thing. You can predict will they both bind or not using these equations. Okay, so now we will also go into one example where people have used, I've shown one example where the lotus effect, which is the physical property of surface, and the surface energy components, that is the chemical property. This is an example where you can combine these both. How about combining physical and chemical in one go? Okay, this is what these guys are doing here. They took a surface made of lignin, a sheet made of lignin, and they introduced nanoparticles. And nanoparticle surface has surface charge and hydrophobicity. because nanoparticles have a surface roughness, that they add surface roughness to this smooth surface, and that is a physical property that they are adding to. Okay. So now here is a procedure. What they do, they take a silica particle, okay, which has a negative charge, and they absorb this PaH cation. So the particle becomes positively charged, and then they add this AKD that adds to hydrophobicity. So you have a positively charged silica particle, nanoparticle, that has hydrophobic property. The positive charge is so that the positive charge, with the help of negative charge on the paper, they stick to the paper, and the hydrophobicity is so that you make the surface, the final surface, water repellent. Water won't stick to the surface, and this is image photograph of water droplet on the surface of this sheet. And this is okay, you guys will learn about this more. Okay, this is a surface topography technique where you can see the surface roughness. Here, when you compare to this, you can see here, which has been modified with the nanoparticles, that it's more rough. Okay, and you will learn more about, I'm talking very qualitatively now, it's rough, it's smooth, but you will get more specific quantitative idea about what is the property that I'm talking about during this lecture. This is an atomic force microscopy image. You'll get information about that later. Okay, so now we have dealt with a couple of examples. Before I end today's lecture, I want you to learn one more concept, which is dynamic contact angle. Okay, so now we have seen that you take a surface, you put a drop of water on that or a drop of liquid, and that gives you contact angle. And because neither the surface nor the liquid is moving, it's static contact angle. But there is also another concept called dynamic. For example, in this case, you have a syringe and you put a drop of water, but then once the drop touches the surface, you still keep pushing some liquid through it. Okay, so that the way this is done is there's a drop hanging from this needle, and then you lower it and the drop touches the surface, and you don't take the needle away. That's what you would do with static contact angle. It touches and then you take it away. But in the case of dynamic, you keep continuing to add liquid. And in the case of receding contact angle, what you do is you place the liquid, and then once the surface has touched the liquid, you suck the liquid back into the syringe. Okay. The information that this gives, I will talk more about it in the next slide, the exact mechanism, what happens. Now, the other way to perform the same thing is you tilt the surface with respect to the plane, and here the gravity pulls the drop downwards. So in this region you have equivalent to advancing contact angle, and this region you have equivalent to receding contact angle. So now if you have a surface, I'm drawing, let's say you have a surface, okay, very rough. I'm talking, let's say, nanometer scale, okay, and you have a surface that is completely smooth. Okay, so now let's say this is the initial drop. Okay, so now when, let's say, you're either, here is a syringe, you're either pushing the water or sucking the water. Let's say you're pushing water. Let's say you're pushing water in. Now this region, because the surface is rough, it gets the evaporation front or the solvent line, it gets pinned here, it gets stuck, buckled. So when you add more and more, instead of this moving here, because it is rough, it gets stuck there. So the drop expands like this. Okay, and so if you measure the contact angle, it's increasing. It's increasing, and then eventually, when the pressure is so much that the buckling mechanism can't hold the liquid anymore, it gives way, and then it goes forward again. Okay, it goes in cycles like this. So this is advancing contact angle because it's advancing. Receding is, let's say you take the same situation where you're taking the liquid up. So now instead of, now as the liquid goes inside, it buckles here, and then it becomes thinner and thinner. The water droplet collapses. Okay, so the contact angle keeps decreasing, and finally it's so low that it jumps from this point to this point. Okay, is the pinning mechanism clear? Okay. Now we'll talk about, let's say, the property where you have buckling happening. Okay, now if there is this spinning process happening, that means there are two things that can be the cause of that. One is you have a surface that has high roughness, as I drew here. The other possibility is the spinning happens either because of physical, which is the surface roughness, the other is chemical inhomogeneity. For example, if you have a surface that consists of islands of hydrophobic and hydrophilic regions, okay, which have different affinity for solvent, then when you do advancing or receding contact angle, each of these islands, they act as the spinning point. So then you get a huge difference between these two, and this process is called hysteresis. Okay, and the way we define hysteresis is the difference between advancing and receding contact. And hysteresis gives you an idea about surface roughness and surface chemical inhomogeneity. Okay, if you take a very smooth surface and if you find huge hysteresis, the only logical conclusion there is your surface is not homogeneous. It's not this. It's either this or this. It's phase separated. Okay, and this is very important when it comes to characterizing surfaces, how uniform surfaces you're making. Okay, so now we'll come to the final slide where I summarize contact angle based measurements. So first we saw the origin of surface energy, and we defined what is surface tension and surface energy, the relation between them, and the methods to measure liquid surface tension. It's using a plate and a ring, and methods to measure surface energy of solid surface, that was contact angle measurement by placing a drop of liquid over it. And we also saw how Young's equation, which relates the surface energy to the contact angle, can be split into the components of chemical interactions, the van der Waals interaction, the acid-base interactions. And we saw the thermodynamics of adhesion, and we also saw how theoretically we can predict whether two surfaces will adhere to each other or not based on surface energy parameters and second law of thermodynamics. And we also saw how physical property of a surface, for example surface roughness, can cause drastic change in surface energy. And one example that we saw was bacterial adhesion, where we try to guess whether the bacteria can interact with a host of surfaces like Teflon, glass, polyethylene, by measuring the surface energy parameters of these both surfaces. And we also saw lignin hydrophobization using silicon particles. And we finally saw dynamic contact angle, which helps us understand hysteresis. And based on hysteresis, you can tell whether the surface is chemically or physically inhomogeneous.